Hey everybody, so I'm going to do a quick example. I want to find the tangent line to the function g of x equals 1 over x when x equals 2. Let's think about what we need here. To get a tangent line, in particular, or any line, and in particular a tangent line, we need a point. We need a point and the slope. Right? Those are our two things. So let's start with the easy one. The point is very simple. We know that we want to find this tangent line when x is equal to 2. We compute g of 2 is 1/2. So that leads us to the conclusion that the point we're looking for, the line is going to be through the point 2, 1/2. So now let's compute the slope. So the first thing I want to do is write down our definition of the slope of the tangent line and this limit that we have defined it as. And so I'll use the notation g prime of 2, right? So we call this the derivative of g at 2, and we can say g prime at 2 or g prime of 2. What it gives us is a number, and that number represents the slope of the tangent line, right? We know the point already. There's an infinite number of lines through that point with all different slopes. So we need to find the one with the correct slope. And this formula that I'm about to write will give it to us. We're going to take the limit as h goes to 0 of g of 2 plus h. Oops, that looks gnarly. Minus g of 2 all over h. Okay. So most of the work we're going to have to do, right? If I try to plug in 0 right now, I get 0 over 0, which is not defined. So most of the work we're going to do right now is to find something equivalent to this expression, this difference quotient, the g of 2 plus h minus g of 2 all over h, that lets us take the limit, right? So I'm going to do this work off to the side and then figure out an expression for this that will work better. So let's compute. Let's look at g of 2 plus h minus g of 2. This is just looking at the numerator for a moment. This is going to give us 1 over 2 plus h minus 1 over 2, right? And I'm also thinking ahead, right? I know that my big problem is this h in the denominator, because that 0 in the denominator is what kills us. It doesn't matter that the numerator goes to 0. The fact that there's a 0 in the denominator is what makes this undoable as written. So I kind of already know what I'm trying to do with this numerator that I have on the right, which is I want to find a factor of h in there somehow, right? As written, I don't see it. It's not clear. So we want to start manipulating these things, doing some algebra that doesn't change what they mean, but lets us write it in a different way, right? And so let's go ahead and do that. There's not a lot of things we can do. One thing that jumps to mind is maybe I try to combine these as a single fraction, meaning I have to find a common denominator. Since these two denominators don't share any factors, their common denominator is simply the product of these two denominators. So I'm going to multiply both of these by 1. All right, and one of them, I'm going to write 1 as 2 over 2, and the other one I'm going to write 1 as 2 plus h over 2 plus h. And so now what I have is 2 over 2 times 2 plus h minus 2 plus h over 2 times 2 plus h. Now I'll bring them together. I've got 2 minus 2 plus h all over 2 times 2 plus h. All right, so we've got 2 minus h over 2 times 2 plus h. And so this gives us negative h over 2 times 2 plus h. Right, so this is starting to look good because I see that I have a factor now of h, right? That h in the numerator, our whole numerator now has we can think of it as having 3 factors: h, 1/2, and 1 over 2 plus h. And then we're just writing them in a convenient way. And there's a negative in there too. But And so one of those factors is h, and that's exactly what we were looking for. So now let's take what we just did and put it over h. Right, all of this over h, which is, of course, the same as simply multiplying by 1 over h. So this makes it more obvious what's happening here. We can cancel those h's out, right? Multiplying by h and dividing by h, or multiplying by h and multiplying by 1 over h, you may as well have done nothing. So that factor can just become a 1, and I get negative 1 over 2 times 2 plus h, right? So this is now going to replace that difference quotient in our limit. So I'm writing down, what did we just write? Negative 1 over 2 times 2 plus h, right? And I want to just clarify something before we take this limit. This set of equal signs I have here in this row, right? This is not strictly true. These two expressions are not the same. That cancellation of h threw out the took away the possibility that h is equal to 0, right? So these two expressions on the left side and the right side of this chain of equal signs are equal only in the cases where h is not equal to 0, right? Everywhere else they're exactly the same. I think I said that wrong, but anyways, everywhere they are the same thing except when h is equal to 0, right? That's the key point, though. For the limit, that's precisely the point that they're allowed to not be the same at. So we can take this limit now. It's a rational function. This h is in its domain. 0 is in its domain. And so we can simply substitute 0 in for h to take the limit. I get negative 1 over 2 times 2 plus 0, or negative 1/4. So I get g prime of 2 is equal to negative 1/4. And remember, this is the slope of the tangent line at x equals 2, right? That's the meaning of the derivative at a point. Okay, so now the tricky parts are done. Let's get ourselves another page. We have the point 2, 1/2. We have the slope. We don't need parentheses for that. Our slope is g prime of 2, which we just computed to be negative 1/4. And so the tangent line, I can write it using the point slope form. Y minus 1/2 is equal to negative 1/4 x minus 2. If you want to write it, I can expand this if I want to. So I'll get negative 1/4 x. I'll get minus 1/4 minus 2 times minus 2 gives me a positive 1/2, and I also have to add the 1/2 from the other side, so I get plus 1. And that gives me the tangent line to this graph at the point y equals 2. Let me open up a graph. Let's graph this thing just to take a look at what it looks like. I'll open up Desmos and share it with you. So here we go. So first let's put in g of x equals to 1 divided by x. We have the point 2 g of 2. All right, let's throw a label on that, 2 1/2, just as we computed. And then our line, which we said was y equals negative 1/4 x plus 1. And we notice this does at least appear to be the tangent line. Let's make this bigger. Let's zoom in. So one of the features of the tangent line, one of the ways in which we can think about the tangent line, right? We have the definition. And the definition of the tangent line is that it's the line that goes through the point in question and has the slope of the derivative at that point, right? That's what our tangent line is. But one reason we like the tangent line is it's the line of all the lines we could have. It's the one that looks the most like our function at this point, right? As I zoom in, the green and the red line, the green line is the tangent line, the red line is our function. As I zoom in, we can barely see the difference between them, right? So this line looks very similar. Let's compare that to something like this. So here's a line through that same point. Let's give it a variable slope and we'll change it. Right, so here, by changing the slope, I'm looking at all the other lines through that point that have all these different slopes. And any other one I choose, when I zoom in, right, does not do what that green line does. It doesn't matter how close I get, it's going in a different direction there. And so it doesn't have this, right, that purple line does not look like it's just becoming the same as as the red line, the function, right? No matter how I'm zooming in closer and closer, and it's always different, right? And there's no zoom where it looks like it's the same thing, right? Now that's not a mathematically precise term, but it gives you an idea of why this tangent line is so special. It's very different than any of the other choices we can make, right? Even this is negative 0.2 as a slope as opposed to negative 0.25. It's barely different in terms of the value of the slope, but we can see that the line doesn't look like the same thing as the function there, right? We can make it even closer. There's 0.25. Now we are looking at the tangent line, but if I add a little bit of values, right, we can see that it does zoom away from it in a way that the tangent line doesn't, right? There's always this little gap that's there. Okay, that is it for that example. Thanks, everybody. I will see you next time.